Find the electric field at the center of the point charges located at the corners of an equilateral triangle 25.0 centimeter on a side as shown in the figure below. Given that Q sub A, that's a charge at A, is positive 2.50 nanocoulomb, the charge Q sub B is negative 8.0 nanocoulomb, the charge Q sub C is positive 1.50 nanocoulomb. Alright, so what are we given? We are given the length of the side of the lateral triangle. That's 25.0 centimeter, and that's equal to 0.250 meters. And we also need the electrostatic constant, so that's 9 times 10 to the 9 Newton meter square per coulomb square. Alright, so what are we asked to find? We are asked to find the electric field at the center due to all the three charges. Therefore, we need to know what the center is. So let's deal with the geometry first. Now we are given the length A on the side is given as A, and that's equal to 0.25 meters. So how do you find the center? If we draw a bisector of each side from the vertex, the intersection of all these three bisectors will be the center of the equilateral triangle. We know this from geometry. Alright, and that center is going to be this point here. This is the center of the equilateral triangle. So how do you find R? What's the distance from the vertex to this center from each vertex? Let's deal with that one. Let's deal with and that angle is going to be 30 degrees to begin with, because we are bisecting the angle, and each angle of equilateral triangle measures 60 degrees, so half of that will be 30 degrees. So theta is equal to 30 degrees. And these are all equal. We know that from geometry. Now, what is the side of the small triangle? The side of the small triangle is half of the length, because it bisects, the perpendicular bisector bisects the side. So each side will have half of the length of the equilateral triangle. So now that we know the adjacent and the angle, we can tell R. We know that cosine of theta is equal to adjacent over hypotenuse. Rearranging for R, R will be A divided by 2 cos theta. Just plug in the numbers. 0.250 meter divided by twice the cosine of 30 degree yields 0.144 meters. So now we know the distance from each vertex to the center. Can we tell what the electric field due to each charge at that center is? To do that, let's do each one separately. So now we know the electric field at A, or due to this charge here, is going to be the electrostatic constant multiplied by the charge divided by the distance squared. Let's plug in the numbers. K is 9 times 10 to the 9 Newton meter square per coulomb squared, and the charge at Q A is 2.50 times 10 to the minus 9 coulomb. Remember here, nanocoulomb stands for 10 to the negative 9. Divide that by the distance from the vertex to the center squared, and that's 0.144 meters squared. That yields 1085 Newton per coulomb, and the direction is going to be downward. Why downward? So now we have positive charge. Positive charge, the electric field will be away, so it's going to be downward. Alright. And what is the x component going to be? There is no horizontal component because it's all down. And the vertical component is the whole thing, that is 1085 Newton per coulomb. Alright, let's do the same thing with charge B. Alright, so what is the electric field at the center of the equilateral triangle to charge B? And that is going to be equal to the electrostatic constant multiplied by the charge at that point divided by R squared. Now what is the direction going to be? Because Q sub B is negative, the direction of the electric field due to this charge is going to be towards it. So how do you find the angle? Now if you draw a line segment parallel to the base, this angle will be the angle of the electric field due to charge B. And what is that angle? This angle is equal to 30 degrees because it's equal to the alternate, because of the alternate interior angles theorem. These two angles are congruent. Therefore, theta is going to be 30 degrees below the positive x-axis, and that makes it negative 30 degrees. So theta is going to be negative 30 degrees. And what's the magnitude? The magnitude can be calculated the same way you calculated the electric field due to A, and that is the electrostatic constant multiplied by the charge at B divided by R squared. Plugging in the numbers, 9 times 10 to the 9 Newton meter square per coulomb square multiplied by the negative 8.00 times 10 to the minus 9 coulomb charge divided by the distance from the vertex to the center, which is equal to 0.144 meters squared. And that yields us negative 3,472 Newton per coulomb, and the direction is negative 30 degrees. That's to mean 30 degrees below the x-axis, positive x-axis, or clockwise from the positive x-axis. So what is the x and y component? The x component will be cosine of the electric field, cosine of the angle multiplied by the electric field, and that's 3,472 Newton per coulomb multiplied by the cosine of 30 degrees, negative 30 degrees, and that yields 3,007 Newton per coulomb, and the direction is going to be to the right because it yields positive. What about the y component? The y component is the electric field at that point due to charge B multiplied by the sine of the angle. That will be 3,472 Newton per coulomb multiplied by the sine of negative 30 degrees, and that yields negative 1,736 Newton per coulomb, and the direction is downward. Alright, so what is the electric field due to charge C at the center of the equilateral triangle? Let's do the same thing here, and that is the electric field at C will be equal to the electrostatic constant multiplied by the charge at C divided by R squared. Alright, so what is the direction going to be? First of all, because Q sub C is positive, the direction is going to be along this line, and this angle is 30 degrees. Alright, so let's plug in the numbers. 9 times 10 to the 9 Newton meter square per coulomb square multiplied by 1.50 times 10 negative 9 coulomb divided by the distance from the vertex to the center, which is 0.144 meters squared. Now, what is the x and y component? The x component will give the calculation yields 651 Newton per coulomb, and the angle is 30 degrees. So what is the x component? The x component is going to be the electric field at the center due to charge C multiplied by cosine of the angle. That's 651 Newton per coulomb multiplied by the cosine of 30 degrees. That yields 563.8 Newton per coulomb to the right. What about the y component? The y component will be the electric field at that point due to charge C multiplied by the sine of the angle. That's 651 Newton per coulomb multiplied by the sine of 30 degrees, and that yields 325.5 Newton per coulomb. And the direction is up because it's positive. Now that we have the x and y component of the electric field due to each charge, we can find the net electric field in magnitude. How do you do that? We add all the x together, we add all the y's together, and use Pythagorean theorem. And here is the process. E sub x will be equal to E sub ax plus E sub bx and E sub cx. Adding them together, that yields 3,570.8 Newton per coulomb to the right. So what about the y component? The y component will be Y component of the net electric field will be E sub A Y, that will be this value here, E sub by, that will be this value here, E sub cy, that will be this value here. Add them together, yields negative 2496 Newton per Coulomb downward. So the net electric field will be, using Pythagorean theorem, E net will be equal to square root of E in the x direction square plus E sub y square under the radical. That is 3570.80 Newton per Coulomb square plus negative 2496 Newton per Coulomb square under radical. And that yields 4357 Newton per Coulomb. And what's the direction? The direction is going to be tan inverse of the vertical component to horizontal component. That is tan inverse of negative 2496 Newton per Coulomb divided by 3570.8 Newton per Coulomb. And that yields negative 35 degrees. So the net electric field, all these charges will be slightly greater or larger in angle than 30 degrees, and that's negative 35 degrees from the positive x-axis. And the magnitude will be 4357 Newton per Coulomb.